Okay, so let's start. So now we got to topology. So I will briefly recall we have this GI inverse system now of finite groups. Then we had this curly G. Okay, then we regard them as topological spaces with discrete topology. And now inside their product, which is still compact, we look at this curly G. Yes, there were those which agree with each other. So here there were also these maps Rij, such that for all I smaller than j, Rji, j, j is ji. Okay, and the theorem that this is closed subset in this product. So then, in particular, it becomes compact topological space with induced topology. Okay. So let's prove it. Not difficult. Proof. I will represent it as intersection of many closed subspaces, basically those given by these conditions. So for each I smaller than G, let G, Ji be this one which satisfies only this one condition. So such sequences such that there is no quantifier here. Yes, so let me emphasize it, just one condition. So obviously G is intersection of them. Over all such tuples. So since intersection of closed is closed, enough to show that this one is closed. Okay, and this is something pretty obvious, but still something is used which is often forgotten. So we look at this G. Now this diagram is not commutative necessarily. Here goes Gj, Gi, Rji, okay, this projection. So it's Rj, I guess, Ri. They were so as you actually notice, this projection maps are continuous. So they are continuous, restricted here as well. Sorry, I'm talking nonsense. It goes from the whole thing. like this. So continuous. Okay, so we are actually looking. At all these elements. So Gij is the set. Now I don't write it in coordinates or x's here, such that Rix, Rijx composed with Rj. Yes, so why this is closed? So I'm saying that such a space is closed because of several reasons.
Well, I was thinking it's an equation.
Uh-huh.
If it was like not equal, I was thinking it should be open.
No, it's equation, so it's closed condition. But still, why is it closed condition? Okay, so we notice they are continuous. This is also continuous. Because anything between discrete. So this is continuous. This is continuous. Okay. But still, not always. This implies that such a thing is closed. So do you remember what is the condition? So the condition is that this space must be Hausdorff, which is usually the case. Okay, so since. But it is often forgotten. So if it was not Hausdorff for some reason, it would break. Okay, which in reality doesn't happen that much. But it's good to know what is used. So since Rij Ri continues and Gi Hausdorff we get that Gij is closed. So that's the end. Okay, and this Hausdorff, okay, is a bit about general topology. So remark, yes, if you have such a situation that you have two continuous maps.
Okay, I understand.
Huh?
Since it's Hausdorff, you can always find open.
Yes, but here is a bit different. Here it's a bit different property. So here, yes, we can this somehow use. So here the set of x's such that f of x equals g of x, which we are interested in, is the same as preimage of y diagonal. Well, this is so this is just set of all yy, and this map is x times x. No, x actually x.
You said preimage, but you wrote y.
Sorry?
You said preimage, but you wrote.
Preimage I wrote, I think. This is inverse. Yeah, and this is x goes to fx gx. So such a set is exactly preimage, and now the condition is actually it's equivalent that y Hausdorff if and only if this is closed in y. Okay, so that's the connection. Just remark on the side.
I was thinking to look at the complement of this, but it's basically the same.
Yeah. So since this is the same, of course, using the definition directly also would give you somehow. But yes, so good to sometimes sometimes when one forgets about such a property, there may be a mistake in your life that in some situation you will try to apply it when it cannot be used. But here, of course, it's applicable. So this curly G is closed, so compact. Okay, so now we know everything. Okay, so corollary, if this is, yeah, I guess it is written already, okay. So, yeah, okay, let me write it again. GI inverse system of finite groups, then inverse limit has this natural topological structure, is a compact topological space. So we have this one more structure, in particular our Galois groups. These infinite Galois groups are like this. So on the top of groups they become compact topological spaces, a bit strange ones, like Cantor said, you see there is nothing connected inside, they are kind of totally disconnected. They have basis of Kloppen subsets, so they are not like the spaces we like, but still topology is useful. It's just not like which we are used, not something which we are used to, but it is still useful. So I think last problem, because just one problem session left, with this topology, you remember if G is any group, then we have this completion map. As I was saying last time, show then the image is dense here with respect to this topology. And this is inverse system of finite groups. Okay. So now the last thing that topology agrees with the group structure. Okay, so let me still define, even if you know what is topological group. So topological group okay, is a pair, so I write it a bit quickly. Where this is topological space, and on this set dot makes it a group. Such that first, just two structures agree. This is continuous, so multiplication understood as such a map, and here we take product topology.
Sorry, I didn't understand this problem 10.
Sorry?
I didn't understand this problem 10. Are you taking all GIs equal here?
Taking what, sorry?
All GIs are equal.
So you know, G hat was this inverse limit by definition. Where GI is normal and finite index.
Ah, okay. Okay.
So I didn't put it. And there was this map basically going to the constant sequence. Okay, not to the really constant sequence, but this map comes from universal property, but physically this map takes G and maps it to the sequence of cosets. Okay. And you don't know that this is dense, so not contained in anything open, which is not everything. Okay. So this is to show. Okay, and here this map should be continuous. And also the inverse map should be continuous. Yes. In many, so it may look a bit strange, this is the inverse map, yes. In many cases, okay, in many natural cases, condition 1 implies condition 2, but not in general. So let's, okay, examples are things we know, okay, most natural, like R plus, invertible elements with times. Yeah, these things we looked at the course about linear groups are topological groups. Actually, they are all Lie groups. I will not explain it, but they have even more structure. They are differentiable varieties, and the maps are smooth.
Rn plus? Is it Lie group?
Yeah, Rn plus as well. You mean this?
Rn plus, I was talking about.
Which one?
It's a Lie group.
Yeah, the simplest one, yes. Yes, addition is smooth. A smooth map, of course. Yeah, everything here. Actually, most of the natural ones are already smooth, although, okay, not. There are some constructions like infinite products, for example, which then are not differentiable manifolds anymore. Similar complex Lie groups, you can put C here, then they have even more structure. And I think in these cases, actually, if I remember correctly, if you have smooth manifold group structure which is continuous, I think this is automatically continuous, maybe by implicit function theorem, even automatically smooth, I think. Something like this. So this often comes for free, but not always. Okay, so those are natural ones. Okay, and then less natural, but the case we are interested in. So, like any even infinite product of topological groups is again topological group. But now really it may lose all the smooth structure, etc. So this is why this thing is a topological group. This one. So topology is product topology, group structure is product structure. And then any subgroup of topological group is again topological group with subspace topology. This is all easy to check. So by all of this, our inverse limit becomes topological group, okay, because it's a subgroup of this product. So for by 2 and 3, and the inverse limit of finite groups is a topological group. Actually, one could do much more general things. One can take inverse limits of topological spaces, they become topological spaces. So in reality, and the inverse limit of topological groups is topological group again by all of this. But we are interested in this case. Something which is not a topological group, but almost. Okay, so I will just say that algebraic groups are not topological groups, but I will not explain too much. So for example, plus is not continuous when we take Zariski topology, if you know, because it's cofinite, here cofinite, and then even diagonal is not closed in the product. So, but okay, it's not continuous when K has Zariski topology. But it's still okay because on the product there is another Zariski topology which is richer than product topology. And with this other one, it is continuous. So it's not topological group, but thanks to that, it has enough good properties. So almost everything works like with topological groups. So if you want, it's a group. Yeah, it's actually a categorical issue. So algebraic groups are group objects in category of algebraic varieties because the product in category of algebraic varieties has not a product topology but another topology, like product in the case, and then it's actually everything is okay. But it's not a group in the category of sets. Sorry, it's not a group in the category of topological spaces. So it's not a topological group. There is a slide. Yes, but it doesn't affect much. For example, those spaces are not Hausdorff. But still, diagonal is closed in this richer topology. Okay, so it's... Sorry? So it's not Hausdorff, but since we consider nicer topology on the product, it's kind of in practice close to Hausdorff. But yes, actually it is compact in the sense, yeah, but this which really fails is that it satisfies this cover property. It's even Noetherian. So it's not Hausdorff, it's like quasi-compact. It's like compact without Hausdorff. And this is bad because you cannot use any properties. Like the continuous maps are not closed, and between topological spaces, image of closed is closed, and here definitely not, like image of hyperbola is open set, line without point. So this is something which really makes it different. Anyway, that's a bit different topic. Okay, that's obvious definition, but this word should appear. So a topological group is called profinite if it is isomorphic as topological group to inverse limit of finite groups. So that's the name. Yes, in particular, Galois groups are infinite Galois groups are profinite. Yeah, and those groups have interesting theory. For example, there are like pro version of Sylow theorems. There are pro P subgroups, such things, unique up to appropriate isomorphism. Many things work in this pro setting. There are profinite free groups. There are pro P free groups. Like Z hat is like free group on one generator, like profinite free group on one generator. So it's not really on one generator, but it satisfies this universal condition that if you have any map sending this one from Z hat to anything in other profinite group, it uniquely extends to homomorphism, continuous homomorphism. Similarly, there are other profinite.
Q is not profinite.
Huh?
Q is not.
No. Q is pseudo-finite, which is another story. But it's so if you are interested in model theory, don't confuse profinite with pseudo-finite, because it sounds similar, which happened to me. Kind of different.
What was pseudo-finite?
So pseudo-finite is like ultra product of finite groups. And this is inverse limit. So different. It's interesting to compare sometimes, but a different thing. And kind of different objects. Okay, so I can state now, I will not prove anything, fundamental theorem of infinite Galois theory. Okay, basically everything the same as in usual one. So we have this Galois extension. Okay, we can also treat finite groups as profinite, just trivially, inverse limit where nothing happens. So I'm not saying infinite. So it really includes usual Galois theory. Yes, big, okay. Is profinite. Okay, then most important, the Galois correspondence is true with one correction. So the map, okay. F goes to Gal and F. So bijection between, so two things. The family of such subextensions of towers now all F, not necessarily finite, not necessarily Galois. Yes, so all possible F between K and M. And then the family of closed subgroups of Gal M K. Okay, I wrote everything, but the rest is basically the same. Okay, let me still write the inverse map. If we take this H closed, goes to fixed points, so invariants. Yes, it's pretty okay. So it's, I guess, pretty clear it should be closed. Because if you take this, so if you take such a thing, you may see it similarly like here, it gives you closed condition. So it fixes something more, becomes a closed condition. So definitely only closed could be considered. And then there is a bit of work, and I think then you use really that M is union of finite Galois extensions. I think at some point that this is really bijection. Okay, so then maybe I will not write, and then the same other properties of Galois theory. Yes, but whenever instead of saying subgroup, which may be something strange, you say closed subgroup. So that's how you distinguish. I have few examples which actually can make clear why do we need, okay, it's already clear we need closed. But also these groups are usually difficult to understand fully. They may be very, very complicated. Okay, so we all the time had this example of FPFP arch. Okay, so we know that this absolute Galois group is isomorphic to Z hat, this profinite completion, inverse limit of all cyclic finite groups. So we can understand it. Okay. So let's understand this isomorphism. We have this completion map. Here, some natural map. Here, and this is this isomorphism. Yeah, so what do you think how Z is mapped into this Galois group, this big one? Similarly as before, Yeah, so there is one special automorphism here, the Frobenius. So that's how it goes. So alpha n is the Frobenius
One goes to Frobenius
in all fields of characteristic P. Yeah? So this is the big Frobenius. So now it has infinite order. So it's really, but it's not all. It's just part of the Galois group, and there are still some others. So let's say that Frobenius I will not put on FP arch.
What are the others? Like, yeah, what are the others?
Huh?
What are the other?
Well, coming from this inverse system, okay, before we believed this is Z hat, and there are many, many more elements in Z hat actually. So if you look at Z hat as this product, okay, ZQ, that Frobenius corresponds to, where to put it, that Frobenius 1, 1, 1 everywhere, and all the others, okay, it's not easy. Can I do something else?
There is 1, 2, 1, 1, 1, 1. What is this?
So somehow if you look at this, okay, so how you get automorphism of this? You present FP arch as this union, and on each part you get some power of Frobenius such that these powers agree with each other.
Okay, maybe I understand. In the let me give an example of an element of an automorphism.
Yeah?
We start with FP and we are looking at splitting fields, so roots. Let us just change the roots in the second level and make everything identity at the others. Can it be possible?
But that could be just Frobenius square. I'm not sure.
But just in second level, like just in...
But what is second level?
FP square.
But it's not really the levels are not like this, they are more like this.
Yeah.
So if you want to fix FP square, then definitely Frobenius square will do it. So really you have to, I don't think you can say it just by one thing. So it must be this inverse system when things are changing. So you really choose on each FPI a power of Frobenius such that they restrict to each other, but are never the same power. So it's not a fixed K such that all of them are Frobenius to K, but they may grow actually. These powers may grow, and this is how you get it. So, okay, maybe. Maybe in problem session we can think about some particular. Yes, but you never will be fully satisfactory like there is a one, like just give it by one formula. You have to give this description.
Maybe I was thinking let it fix one chain and do whatever else.
So okay, so I guess good example would be what is, for example, 1, 0, 0, 0. Oh, this is fixing one chain. Okay, so like this first one I guess corresponds to Q equal 2. So you look at FP square, FP4, FP8, FP16, and then you put, okay, and here you put Frobenius in this level, and then you don't. So this will correspond to this.
Okay, but what do you do with other chains?
Identity.
Identity, okay. Okay.
And then I think this will correspond Yeah, this should correspond to this. Yeah, for example. Okay. So alpha is described. Yes, and I was okay here saying that. Okay, phi, this I of n, is always I. Okay, maybe it's iota. Is because those are these finite index subgroups, and the psi of sigma should be okay. Fi of sigma restricted to Fpi, where Fi gives isomorphism on finite level. So basically you restrict to Fpi, and it must be power of Frobenius, because on each finite field there are only powers of Frobenius, and you look which power, and that's how you get your sequence. Okay, so we are asking about inverse process, how from a sequence which agrees with each other, so it is in the inverse limit, gets such a sigma. So it goes both ways. So I have one example which actually to calculate takes a bit too much time, as I noticed my lecture in Poland. But then just briefly, okay, we have this. Let us now say it's equal. So I'm asking what corresponds to the ZQ. And actually, I'm looking to something else. Fix R in P and consider HR. So it will just piece this coordinate, which is R. So 1 prime is fixed. So now I'm saying that the fixed points are actually exactly as the ones we discussed for R equal 2. This will be this chain. Now increasing union which maybe can be called, although I never seen it like this, my private notation. So I'm putting.
We see this HR as subgroup as in the art coordinate it's 0, right?
0, yes, nothing.
To see as a
yes,
subgroup.
yes. So I'm just saying yes, there is nothing in this coordinate. Yes, so it should be like this. So quite a big subgroup gives quite a small subfield, but still infinite, because this one has infinite index. So again, index corresponds to the degree of extension. This was one of the properties I didn't say. And this is somehow, and if you just took one ZQ here, then it would be something opposite as fixed points. Compositum of all such fields except the one you choose. So this is what happens on this infinite level. Yes, so also you can think that kind of FP-alge. Okay, now I don't have a good notation. Now this means compositum of fields. all this which can be obtained as chains, and then the union compositum is everything. And it kind of looks like this, but the correspondence is rather opposite. If you remove one thing here, so take what remains, then you get one thing here, and kind of vice versa. Okay? So maybe this may be okay. Maybe not simplest, but one of the simplest examples of Galois infinite correspondence when it really matters what is infinite. Yes, and also it's quite clear that Z itself doesn't correspond to anything, because Z corresponds to Frobenius, and the fixed point of Frobenius is just Fp. But it cannot be, so the smallest possible field. But Z is not the biggest possible group. There are many, it's countable, and Z hat is uncountable, for example. So this, but it's dense. That's why it really gives you the same as its closure. It's another property. So if you try to go like this with non-closed group, then here you get M of the topological closure. Okay, so invariants of a subgroup are the same as invariants of its topological closure. Because you can take invariants of any subgroup.
Invariants of subgroup?
Yes, so here, in this way of, yes, so in Galois correspondence, you have this sub-extensions and subgroups. And one way is taking this Galois, another way is taking invariants. So I'm saying that the bijective correspondence is between sub-extension and closed subgroups, but still this map is well defined for any subgroup. So it's just not bijective because it coincides with the closure. So it's similarly like there. Okay, I think we have a break now.